Okay, hello everybody. So this problem is about the center of mass. And so we're actually just going to get rid of the one-dimensional wire and just ask you to compute or explain the center of mass for a surface in R3. So first a picture. Let's say that this is some surface in three-dimensional space. And let's say I want to balance it on my finger. So maybe here's my hand, here's my thumb, and I'm trying to balance this. And right there, this point where I can balance it, that is the point x bar, y bar, z bar. And it's the center of mass of this surface S. Okay, so it's the point where you can balance it. That's the center of mass. Now, let's put that in words. The center of mass is the point, or really I'll just say is a point, a specific point, usually called like that with bars. And how do we compute that point? Well, first, you need a density function. So this surface here, it needs to have mass. And in order for it to have mass, you need to know how much mass per volume. Like it definitely has volume in R3, like this piece has a certain surface area, a two-dimensional volume. But we want to know, like, is the material really thin here, or is it very thick here? And is it a lot of mass in this little volume, or is there just a very thin, paper-thin surface that has almost no mass in that volume? So first you need a density function. And so usually this is denoted by Greek delta for density, and it just takes gives a real number that measures the mass per volume. And by volume, as always, I mean whatever dimensional volume makes sense. So this is really a two-dimensional volume of our surface. So this would be a mass per surface area, you might say. Why? Well, because we have a surface in R3, a two-dimensional surface. Okay, so you need this. This is given to you. You have to know how your material is made, okay? How much mass is on each point of the material. Is it very thick here with a lot of mass and very thin over here? You need to know that. Next, you compute integrals. And what are those integrals? So the formulas is that x bar should be literally a number, like 2.3. It should be the x-coordinate of this point right here, where I can balance. And what number is it? Well, it's going to be the integral over the surface of the function x that takes any point in space and gives you the x-coordinate of that point, times the density, divided by the integral over the surface of the density. So this is a number, and we divide those numbers and get this number. Okay. And similarly, y bar will take the integral of the y-coordinate times the density divided by the integral of the density. This, by the way, will be the mass, the total mass. Z bar is equal to, well, I guess you can probably guess it at this point, but let's point something out in words. This number is the total mass of the surface. So the density says mass per volume, and then integrals multiplies by volumes, giving you the total mass on the surface when you integrate over the whole surface. Okay, and it's the same formula in the denominator. This is the same number, it's the total mass. Finally, z bar is now we average the z coordinate weighted by density, and we integrate that function over the surface. And then we integrate this function over the surface to get the total mass. Okay, so that's all. As you can see, you need to do two integrals to get one of the points where you can balance an oddly shaped, possibly a various density material surface. And if you need to figure out where it will balance, that you have to compute, I guess, 6 integrals. Well, this is the same in denominator, so really you just compute this once. And then you compute these 3 integrals, which are all different. So really there's 4 integrals you need. Okay, so that's an application of integration. Notice I didn't mention the density function at all in the question. You need to know that in order to get the center of mass, you need some density function. And you see that this density function gets multiplied by the coordinate function, and that's what you integrate, because you can only integrate a function here. So by the way, like when I write y, what I really mean is the function that takes a point in space and spits out the y coordinate. So it would take the point 4, 2, 1 and spit out 2. Okay, and so that's what this means down here. Okay. That's all.